So it's a kind of talk that I give fairly frequently because it says work in progress, but the emphasis is on work. There is a lot more work than there is progress. And some of it is joined with categorify. And when I was thinking of how I'm going to teach this talk, I figured, well, it's the last talk of the day, so I don't know how much attention people will be paying. So I decided to put sort of the question that I really wanted people to think about first, and then the motivation later. Maybe it's wrong. I don't know. So let me start with, I'll just put so first I'm going to talk about the combinatorial setting. And the statement of the problem. It's going to be big, but it will get less vague as we go on. Then I will talk about the physical meaning string theory motivation. And 3 and 2 slightly related. I'll see what's known so far. I'll say what's known so far. And possible approaches, if time permits. We'll see how far we get. So the combinatorics of the problem is extremely basic, very flexible, which is kind of what I like about it. You start with a lattice, by which I just mean a free abelian group. And I start with some kind of lattice Polytope delta. Bounded lattice Polytope of maximum dimension. And by this I mean just a convex hull of finite set of vertices in my lattice. Just a polytope. I mean, even something like this, a segment of length 2 in Z is good. Then I'm going to consider a cone over this polytope. So I raise my lattice. I get an extra direction, and I'm going to consider cone C, which is just r greater or equal than 0 of delta comma 1. So the way you should think about it is I have my polytope delta. It's a lattice polytope, so there's a lattice vertex. Maybe there are some lattice points in the middle. And I raise it to height 1 and I do a cone over it. Right? But delta is completely arbitrary. It's not reflexive, if you know what I'm talking about. So let's look at all the lattice points, V1 through Vn, are lattice points in my polytope delta. Basically, this is V1, V2 up to Vn, however many. And I'm going to consider V, which will be a base of all the families I'm going to be talking about. And it's the set of antiples of complex numbers such that if you look at a degree 1 element in the semigroup ring of the cone intersect with the lattice. So when you have a lattice, you have a cone, you can look at all the lattice elements inside the cone. They form a semigroup. Out of them, you can build a semigroup ring, and then this one's graded the way it's constructed, and a general degree 1 element is just a linear combination of elements, monomials that correspond to the VI's with some complex coefficients. So I'm looking at such that are generic. More technical term is delta non-degenerate in the sense of Vaterev, but it's just some kind of Zariski open condition. All right. Perfect. Switch boards. Now, I'm gonna, I promised you hypergeometric systems. So whether you like it or not, I'm gonna define them. So there are gonna be systems of linear PDEs. Yes?
I'm sorry, can you explain this condition?
Oh, delta non-degenerate, what's the...
No. The condition about x1 dots xn.
Oh no, so beta, so B is a Zariski open subset of Cn, which consists of points such that if you look at the degree 1 element in the semigroup ring with those x's as the coefficients, then it's generic.
So the first condition is not a condition.
It's not, no, it's just, no, such that, you know, no, yeah, it's not. Okay, so I'm going to define some, so we're going to define the following systems of PDEs. System of, eventually there'll be 2 of them, but let's talk about one of them first. The system of PDEs in variables x1 through xn. And the way I call them is BBJKZ. BB stands for better behaved. Another alternative term would be like normalized JKZ, but I mean BB sounds better. People who do JKZ hypergeometric systems professionally, they couldn't care less about them. They're too boring, but you know, like these are the ones that are relevant for mirror symmetry. Okay, so anyway, so what are they? The way I'll state it first is as a system of countably many equations on countably many functions. But you will see pretty quickly that it's really can be rephrased as finitely generated D-module. So finitely generated, finite number of PDEs on finite number of functions. But anyway, the functions that I'll have will be some functions phi c of x1 through xn, where C will be in my set, so in the cone, the lattice point of the cone. And now here are the equations. Oh, I should say that x1 through xn will be in this space B. Okay? And the equations are the partial derivative of phi c is phi c plus vi. Yeah. you already see from here that you really can reduce to finite number of ICs, but this just looks nicer if I consider all of them. And then the second equation is the sum. I'll explain the notation in a second. Yeah, so the first is makes sense for all C and C intersect N and all I. The second one makes sense for all C and C intersect N and every linear function from N to, I don't know, C. But you can really just pick a basis. Okay. So the first one is kind of weird. The second one is some sort of homogeneity condition with respect to an action of a certain torus. Fine, it's a system of equations you can prove without too much trouble.
So the second equation has the same C, right?
Yeah, of course.
So something.
Yeah, I could. Yeah, it's just saying that phi C has the certain weight with respect to the torus, and it's compatible with the first one in the sense that if it's called for phi C, when you differentiate, it will work just fine here.
And the second summand, does it correspond to the extra dimension that you have in your extended data?
No, actually, the extra dimension, no, I mean, I don't. No, no, it's for any. So in particular, it could be the extra dimension, but it could be something else. Mu could be the height function, but it doesn't have to be. So it's easy to show that the space of solutions in a neighborhood of any point in B is, and it's a vector space, of course, and dimension is equal to normalized volume of delta. Normalized in the sense that the basic simplest is normalized to have volume 1, and so you have this local system for meaning vector bundle with the holomorphic bundle, vector bundle with a flat connection, the space of solutions to this system of equations. If you've seen what a usual GKZ is, it's sort of similar. You start with a single function, and you have, which would be phi 0 in this case. You have some kind of homogeneity condition, and you have a condition that every time sum of VI's is equal to another sum of VI's, there is an equality of partial derivatives. So the usual GKZ is a relative of it. The usual GKZ can have dimension spaces which are higher. It can jump up. And somehow this BBGKZ gets rid of this nonsense. Well, it's nonsense for me, but it's people who study it related to like local cohomology and who knows what, more like commutative algebra than algebraic geometry. Okay, so there is one system, so we will call this BBGKZ of C. And you can do a similar thing, replacing C by its interior. So similarly, BBGKZ of C interior is defined as follows. You have some kind of functions, psi d of x. D now is in the interior. And the same equations.
So if you put it over the reflexive, is it equivalent to?
If they're reflexive, they're not quite the same because of the shift. So you would have to put, in principle, in the GKZ, you put also some kind of parameter beta, and you would stick beta in here. And then in the reflexive case, one would be this, and one would be with the beta. And the way you should think about one and the other, it's if you have a semigroup ring, C of C intersect N, then when you look at the interior, that's the canonical module for that ring. And we will see later that these are dual local systems, meaning that there is an actual way of, one is naturally, fibers of one are natural duals to fibers of the other. Okay, now, how does this have, what does this have to do with any sort of derived, oh, I forgot to say, it has the same dimension of the space of solutions. Now, what does this have to do with the topic of the workshop? Well, the problem, it's a very old problem for me, is to construct isotrivial families I'll call them d sub x and I don't know, the sort of the 0 of x of triangulated categories. So that when you pass to complexified zero groups, these are the solution spaces in questions, are the spaces of solutions to, for reasons, I don't know why how notation is set up, but somehow it's the opposite. It actually goes this way. Now, as stated, is kind of stupid, right? So I better tell you what so isotrivial means the following. Every fiber is the same triangulated category, but there is some monodromy. As you go over loops in the base, you get some autoequivalences. But I really, like if you think of analogy of Riemann-Hilbert correspondence, you can, if you want to define local system, you can say, well, it's a representation of the fundamental group, and from there you get a local system. I don't want that. I want an actual definition of a connection, right? Derived category maybe in the world of D modules, and then like everything's D modules, all the objects and all the morphisms move in the neighborhood, and my analytic continuation is then intrinsically defined, although obviously computing it is a different story. Right, and what are they supposed to be? So this is going to be some dB Koch, I'll just say dB of certain Kraft resolutions of affine toric chloride. And this is going to be something like this, but supported on Well, the notation will make sense later, supported on the preimage of the closed torus orbit.
Is sigma the normal term? Is sigma the normal term?
Yeah, oh, yeah, sorry. Yeah, so right. So what is sigma? Sigma is some simplicial refinement. No, not normal. No. It's a simplicial refinement of C. Anyone will do, and this is the corresponding smooth Deligne-Mumford stack. Maybe a variety, maybe not. I'll give an example. So maybe I'll say like the upshot. There are various derived equivalences, and in particular by Kawamata, if you have two different toric Krappin resolutions of a toric singularity, they are derived equivalent. What I'm attempting to do is to realize this derived equivalent as sort of a continuous operation. Instead of just a finite sequence of whatever, instead of some kind of finite sequence of wall crossings, I want to think of some kind of continuous analytic continuation, if you wish, from one to another. Okay. Now I'm gonna.
Are you asking that they have the same monodromy? It's a differential equation, or is it also using the
No, so I mean, monodromy, some of it would be kind of hard to compute, right? Because the base B, it's a complement of this A discriminant, so it could have rather complicated monodromy. So yeah. No, but I would definitely expect that monodromy should give me autoequivalences. In some, like parts of the monodromy I understand, like I see how the tensoring by line bundles comes in, but that's not. So now let me describe the motivation. I promised you physical motivation, but there has to be a caveat, right? It's not what physicists think, it's what I think physicists think, which may or may not be the same. But, yeah. But I do have a reasonably good authority that they do think that such a thing should exist. At least if I understood Eric Zaslav's comments correctly, which I think I did. And no physicists have yet contradicted me, so that's also good. Right. Well, so in physics world, one of the kind of objects of interest is so-called n equals 2 pseudo-conformal field series. I have no particular desire to explain what they are. It's a particular case of something called quantum field theory, which isn't really axiomatized. And I think for a physicist, like, they wouldn't want it to be axiomatized, because what if they decided all of a sudden to change it? Right? So mathematically, it's not particularly well defined, but all the physicists know what it is. And so, in particular, they don't just come in single, like they come with some parameter spaces. So you have this some kind of finite dimensional parameter space of n equals 2 pseudo-conformal field series. And I'm gonna write it as some sort of bundle, and each fiber is n equals to 2 SCFT. Well, fine. Okay, we don't understand what this whole thing is, but we understand some mathematical aspects of n equals 2 pseudo-conformal field series. So in particular, if you look at open strings, then they come with two categories. One is like B brains, and the other is like A to A brains. So in particular, but anyway, let's just focus on one of them. So you have some family of triangulated categories that comes out of this. And the consequence, there is same picture, right? Some kind of base, some kind of parameter space. And then I have my triangulated categories. For reasons that it's kind of, I mean, I don't want to claim that I'm absolutely sure that it's always the case, but in many cases of interest, the parameter space is a product of two parts: the complex moduli and the Kähler moduli. So there's a complex parameters and there's a Kähler parameters. Whatever that means. And in particular, the interesting statement is if you fix a complex parameter and if you vary the Kähler parameter, then your triangulated category should locally be the same. Globally, you may have monodromy, but locally, it should be the same. For a fixed complex parameter and varying Kähler parameter. There should be this isotrivial family of triangulated categories. Something like this. And I'm writing some kind of weird base and whatever. And you have some kind of family of triangulated categories. Now, if that's all it was, mathematicians would never be involved, or geometers would never be involved anyway. But the point is that physicists can, in some cases, express their n equals 2 superconformal field series in terms of maps to some maps from curves to some, or from Riemann surfaces to some geometric objects, right? So another way of thinking is maybe, okay, maybe in this region we can express n equals 2 superconformal field series in terms of x1, and then maybe in some region here, maybe it overlaps, maybe not. You can do this in terms of x2. And when these things happens, the triangulated category in questions becomes dB of x1, and this becomes dB of x2. And I'm writing an example where x1, x2 are, say, Calabi-Yau's, but you can be more flexible than that. Maybe one is a variety, another is the Lie-Mumford stack, maybe one is so-called Landau-Ginzburg model, and then you're going to get like derived category of singularities on the other side. But a lot of derived equivalents that you see in the literature are actually physically something like that. There should be some family that under some family of superconformal field series, such that in one region you can write this technical term is type 2B branes, some kind of boundary conditions on open strings, and the derived equivalence is expected because of a picture like that. I wrote 2, but there could be any number of them. Okay? So obviously I'm interested in realizing this picture. So if I were to do it, where would we look? Like, what's the easiest example that where one could try to realize it? And for me, the easiest is that. And physically, this is what they would call abelian gauge linear sigma model without potential. I mean, this without potential, this is what causes me to have non-compactness. So I paid the price for the non-compactness by having 2 categories, not a single one, but sort of. But that's okay. That's not a big deal. I still feel that this is the easiest setting. So this is basically exactly this the GKZ story. All right, so that's the motivation. Now let me explain which are the derived categories, which are the triangulated categories that I want to do there. Let's see how we do this. I don't know how useful this is. I'm going to erase that. I'm going to leave the top, and I'm going to erase this part, unless there are any objections. I mean, in principle, one could just say, okay, we have derived equivalence, and then we want to realize it as this analytic continuation. But I really wanted to put it out there that a lot of derived equivalences are like this. Even statements like that the quintic versus category of singularities, like the same. That's all part of this picture.
Your expectation about Hodge numbers, when the Hodge numbers should stay the same.
Yeah, absolutely. But Hodge numbers should be usually easy to prove, right?
So they believe that you should derive invariant Hodge number.
Oh, that's how you're. I don't know. Actually, that's a good point. Yeah. Good point. All right, so let's see where are we. Thank you. Yeah, so and then if you have this isotrivial family of triangulated category, when you pass to the K0, you're going to get this lattice, and then you're going to get the, and then you're going to get the local system. All right, so what's the geometry? I still have my, I don't have my picture. Ah, I'm supposed to draw it, correct? Yes. So we have this cone. I'm going to draw it this time just like that, and my segment will be just length 2 segment. And this is my cone C. What you can do, so the toric variety is the one defined by this as a cone in the lattice of co-characters. So the toric variety is you take the C dual, intersect the homomorphisms from N to Z. You take this semigroup, you take a spec of the semigroup ring. This is exactly what you would have if you ask for affine Gorenstein toric variety up to some factor of the torus. So the Gorenstein really correspond to this grading condition. Okay. So you have this variety. This is the spec of C of C dual intersect and dual. And it has multiple resolutions of singularities. This, in principle, it would be stacky resolution. The important thing is the Kreppen. And there is one-to-one correspondence to the one I'm interested in is they correspond to triangulations of delta. There is a technical regular condition that corresponds to projectivity of these varieties. I don't really know what happens if you drop it. It wouldn't quite be part of this picture. But it doesn't matter in low dimension and already unknown in low dimension. And I'll give you an example. If my delta is a segment of length 2, my cone is this. There are two triangulations of delta. One is just to nothing. And I'm not using the middle point. I don't have to use all the points. And the second one is this. I'm gonna look at the corresponding refinements of the fan. And this will correspond to the quotient of C2 by Z2. This corresponds to O of minus 2 on P1, so smooth scheme, and they're both resolution of the A1 singularity. You have this A1 singularity here. This is the usual resolution when you blow up and you get the -2 curve, and this is a stacky resolution, and it's well known that these two are derived equivalent. And the general construction is pretty much, it's pretty much straightforward. You have this triangulation, you look at some JT quotient of C to the n by the group of essentially of relations on those VIs, and you construct, and then depending on which triangulation, you're gonna put different stability condition, and you get different triangulations. Physically, it's kind of a rough approximation to the true moduli space. So you have to kind of believe me that there is more to physics than just variations of GAT. For example, in this case, when you have, my parameters x1, x2, x3, then the condition on B is, not surprisingly, that, right? And in terms of this parameter, x1, x3 over x2 squared, well, it's not equal to 1/4, right? Well, I mean, there's a C star, but also this one is not equal to 1/4. If you so physically, the scalar moduli space, it's kind of like C star with also this 1/4 removed. Variations of JT don't see the 1/4. It's like a positive or negative. So it's a little different. It is a little different. This is some sort of instant on contributions. Not sure why. All right. Okay, so where are we? Right. Well, when I make the statements, it's like, how do I know that this has anything to do with this BBJKZ, right? Why? Well, one can say that this is sort of inspired by the mirror symmetry, because physically, the mirror of this is going to be some kind of potential given by this sum of xi vi. I never was quite able to figure out what the correct Foucault-sidal category is on the mirror side. And I talked to Abu Zaid, and I'm not sure if we agree, whatever, but there's something there. There's some sort of something on the other side, and in particular, this is roughly a Gauss-Manin connection of some periods of hypersurfaces in toric. Roughly, because there are some technical issues which we haven't quite figured out yet. So that's already encouraging, but there's a stronger statement, and now I'm going to switch, erase. There's a stronger statement which goes back to the pieces of Paul Forja around 2000. Which kind of gives a very strong indication that these BBJKZ are the correct answer to the K0 of these mysterious isotrivial triangulated categories. Yeah, so while I'm erasing, I can be just musing like, what could they be? Well, I don't know. What I'd love to do, I'd love to construct some kind of, for given x, construct some A-infinity algebra or something, which would maybe in the category of D modules, and so that everything would make sense locally. But once I move it, I might have to like rewrite it as a different algebra. I don't know. If I knew, it would be work. Wouldn't be just work, right? Okay. Now, so first is Paul Forja, and then some of it with me, and then I think the final nail in this coffin was my student Zingri Han. And so in some region of parameters, solutions to BBJKZ can be expressed in terms of the K theory, the K0 of the corresponding stack. So this is in some region. Roughly speaking, when the sizes of the coefficients xi, their logarithms are convex, very convex in certain sense. Convex with respect to the triangulation. And if you have two different triangulations which are next to each other, in the secondary fan, meaning you just have this generalized idea flop going from one triangulation to the other, then if you write this thing, this will be solutions to BB, GKP of C. These are dual spaces, whatever. And here there is an isomorphism induced by pull-back, push-forward equivalence of by Kawamata. So it's not that in general you're going to get pull-back, push-forward, but for just single generalized idea flop, you could have pull-back, push-forward, I guess push-forward, yeah, pull-back and then push-forward, the equivalence. So this induces isomorphisms on the derived category, and then the diagram is completed by taking analytic continuation of solutions. So Paul Horja had it in the case where there's a varieties, and then we extend, but this was before the BB-JKZ was defined, so it was for usual JKZ. Then we extended it to stacks, and then finally this is what was done in general. Oh, and then you have the same diagram for the, I didn't say what the other category is or whatever. There's another one, it's supported on the pre-image, it's sort of compactly supported, but not more precisely. It's supported on this compact, on the compact torus orbits on the resolution. So complex is on the whole space, but the cohomology is supported.
Can you say again what's happening on the top line? The two sets of solutions are on different regions.
It's analytics, yes. So you have this. So the regions they're sort of adjacent. They look like this, and then you can do analytic continuation from here to here, and then you get. And it's Mellin-Barnes transforms. It's as ugly as it sounds. There's a reason I'm not writing down the gamma solution. It's not super bad, but only because I've been working on it for so long. The first time I saw it, I really didn't like it. Anyway. But it is a natural thing to write. It's a natural way of writing. So the original GKZ already had gamma solutions, and this is once you kind of make everything more, build it up, like it naturally is the same to do. If you see things like gamma conjecture, like this is actually one way to motivate gamma conjecture. It really naturally appears in this picture. Okay, now, the one thing that keeps me reasonably motivated to continue here is that I really think that I'm just an idiot and there is some kind of simple formula for it. And to explain why, I'll give you an example. When we wrote this BB-JKZ and BB-JKZ of the interior in 2014 or something, they were supposed to be dual. We knew they were going to be dual. But we couldn't prove it until like a year ago. So, and then just, it's the kind of thing when once you see a solution, you think, oh, it was just stupid, right? So let me just, or at least the solution has a formula. I mean, there's a reason why it's not so easy to come up with it. But let me tell you why BB-JKZ and the BB-JKZ of the interior, why they're dual to each other. So what you do is you do the following. First, you pick V in C generic, really not a lattice element. And I'm going to define the following gadget. So I'm going to look at the sum over all subsets of indices of size equal rank n. Sum over C in one cone, D in the interior lattice points, which add up to the sum of those VI's, the generators. Now here I'm going to have a product of xi for I in this set. Fine. I'm going to have the volume of the span of these VI's, phi c psi d, times some slightly mysterious psi cdi, where psi cdi is -1 to the degree of c, so the degree shows up. If for epsilon going to 0 plus, c plus epsilon v, d minus epsilon v lie in the cone spanned by the I, in this set, and it is 0 else. So this is really not horrible. You have two solutions. Remember, for every lattice point, there's a corresponding function in variables x. And I declare this pairing of them to be this. It's clearly bilinear in phi c and psi d. But what's nice is, first of all, this pairing is always a constant. So in other words, independent of xi. Right, this is what you expect from the pairing of the local systems. And it's a constant. Under gamma identification, so gamma identifies solutions in some region to dual to K0. There's a similar one for the interior. Is going to be dual of the K0 supported at the compact torus fiber, torus orbits. And under this identification, this pairing is the inverse of the early characteristic pairing. Up to some constant, that's just a matter of how gamma was defined. And in particular, this was also independent of V, independent of line.
Okay. So in which angle will the pair up some kind of completely support objects with all the characteristic of the category?
Yeah, so right. So you have to have completely supported with all, exactly. Right, then it makes sense. Like if you do it compactly with compactly, of course you can do it, but it's not going to be perfect pairing. But this is a perfect pairing. And like the funniest thing, like the first statement, it's like 3 pages of like undergraduate level arguments. There's really nothing there. Just to prove it's a constant, you differentiate and mess up with your sums and a little bit of geometry, convex geometry, and you have it. Now that's ugly, as you can imagine. But again, not horrible, because once you have this, then there's a monodromy. If you are in this region, and so it's a region is about the absolute values of x. If you let the argument of x, if you let x go around the origin, so keep the absolute value but change the argument, you get twists by the line bundles. So then this monodromy really helps you in this situation, because both things behave nice with respect to monodromy, so it's fewer things to compute. And then this just follows from that, because this has nothing to do with it. I have what, 2 minutes about that? Perfect. This is the part where I'll say, how one can try to construct those triangulated categories. Yeah, I don't want to. My motivation comes in part from some computations like vertex algebra 1 years ago, but again, this may be misleading, to be honest.
What you're erasing, the pairings, do you mean by inverse, do you mean minus or 1 over?
No, so those are. By inverse, I mean that you have a pairing on K0, and this is a pairing on the duals. So in terms of the matrix, it really would be an inverse.
Yeah, okay. Yeah.
So the difficulty about finding this is that phi's and psi's, they satisfy a bunch of polynomial relations on themselves. So there's never going to be like a unique formula. And the way this comes about is one day Zingri came to my office and said, well, there is this paper of Fulton and Sturmfeld where they compute the class of the diagonal for a toric variety. And it has this formula in it. It looked different, but basically, after that, like, after 2 days, we knew we were going to have it, right? But anyway, so somehow, only have nothing, right? So here's the first missing step, which I feel like if I have it, I'll have the rest of it. Okay. So somehow I have to associate. So I have to associate to spec of C of t something like this. Z greater or equal than 0 in Z, and the spec of C of t inverse, I have to associate, not just, but like, d of this. Let's say d. I have to associate just a 0 in Z in a way that localization means getting rid of this extra stuff. If I could do that, I'll probably have the whole thing. It's sort of algebraic way of putting what symplectic geometers call stops in their final categories. But I've had some ideas. I'm still working on it, obviously. Like one way one can do this one, for example, is you can take C of Ts, so this is S. T is in the dual lattice. And maybe epsilon and epsilon, this is odd. So no squared is 0. And it's a DG algebra. Yeah, so obviously everything should be like DGOA infinity. And the differential is S G of T. Yeah, this is just quasi-isomorphic to C of T, which is sort of obvious. But if I just try to get rid of S, I don't think you get C star. So something's missing a lot maybe in my picture. It's motivated by some stuff in vertex algebra where I had something which was on one hand sort of invertible, on the other hand it was sort of nilpotent, and at the same time non-trivial, right? So I'd love to have something in this DG setting that also sort of both invertible and locally nilpotent, and I don't know. But you know, the fact that it took us 8-9 years to do that makes me think that maybe it's just dumb, and you know, tomorrow I'll figure it out. That's it.